This is a sound check. Make sure you can hear my voice. You don't have to. You can put this on mute. But if you want to hear the explanations, I'm going to be speaking them. Please read this first. Basically, all it says is grade yourself honestly, take the whole test before you look at the answers, and then send me your score no later than Monday, the 6th. Starting from question 1, it asks which of these two pairs of graphs is basically consistent with each other. And to understand what we're looking for, you look at these two words here. Uniformly accelerated means that the speed is changing at a constant rate, and therefore we need a slope on a speed versus time graph that is constant, or a straight line. So that's going to eliminate answer choices B, C, and D. And then we just want to look at A and E and figure out which of those two shows two graphs that are consistent with each other. And on A, we start off with a positive slope, go to a less positive slope, and then at the end we're approaching a slope of 0. You drew little tangent lines on the graph. And the tangent lines of each moment would be the derivative or the instantaneous rate of change at that time, and that would be the speed graph. So A is wrong because if you wanted to match this distance versus time graph, you would have started with some positive speed owing to the positive slope at the start here, and then it would have steadily decreased down to a speed of 0. That means E is the correct answer. Question number 2 is going to allow us to make use of the elastic collisions idea. If you haven't already, you should go back and watch lecture number 6, which is also on the YouTube channel under playlist number 9 about momentum and impulse. This is a question that allows us to make use of the 3 things that are conserved in any elastic collision. So let's first review what those are. Alright, so these 3 things are conserved: relative speed between the colliding objects, linear momentum, and kinetic energy. So linear momentum, remember, is conserved in any collision because we make the assumption that a negligible amount of time passes during the collision, so that even if there is an external net force, it has no time to change the momentum of the system. Only for that instant during the collision, though. So what does each of these 3 things mean formulaically? Starting from relative speed, that means that the speed at which A is either getting closer to B or farther from B is the same before and after the collision. But you'll notice we've inverted the subscripts. So what was once A minus B becomes final velocity of B minus the final velocity of A, where again these prime notations are not derivatives. These are not calculus notations. These just mean after the collision. The reason the subscripts change order is because of the change in relative direction. So if 2 things are approaching each other and then collide, then after they will be moving apart from each other in an elastic collision. All right, linear momentum being conserved is a formula we've seen many times. I don't want to go into that right now. And the same is true of kinetic energy. We're just going to use 1/2 mv squared. Sum the energies before they collide. Those will be equal to their sum of energies after they collide. So we're going to end up needing 2 different equations here because we have 2 different unknowns. We don't know the final velocity of A or the final velocity of B. And therefore, you need 2 equations to use a system of equations and solve for 2 unknowns. You can use any 2 equations. It doesn't matter. But I'm going to use the 2 that look the simplest. So relative speed has the fewest terms. I'll keep that one. And then linear momentum has fewer terms than the kinetic energy formula, but it also simplifies further in this question because the mass of A and the mass of B are the same. They're both 4 kilograms. And therefore we can cancel out all of the m's here. Also, it's just an error that I put prime on m because there's no such thing as the final mass. I mean, in this question, it's not like the masses of these blocks are changing, but that's not important. So now that we know that we have these 2 simplified formulas, cutting the m's out leaves me with VA plus VB equals V prime A plus V prime B, and we can now solve this using a system of equations. So the question says, figure out V prime B, or the final velocity of the block that was in the middle of the image after the collision. I want to actually do something different. I want to show you how to find V prime A, and it's because you get a really interesting result if you do that. That can save you a lot of time in the future during elastic collisions. So here's our 2 formulas, side by side. On the left, we have relative speed conservation. On the right, we have the simplified version of the momentum conservation where the masses have canceled out. Because the initial velocity of block B is 0, I can plug that in on both sides and then solve for VA. Since these have already both been solved for VA, we can take these expressions for VA and set them equal to each other. Then there's a positive V prime B on both sides. Subtract that out, and you're left with negative V prime A equals positive V prime A. And therefore, the final velocity of block A, the one that was initially in motion, must be 0. This leads us to a conclusion that can save us time. So we're going to specify that if two preconditions are met, we get a really interesting result. First condition is that if and only if two objects have the same mass, and if and only if the collision is elastic, then the result is that the objects trade speeds. Therefore, the final velocity of the block on the left, once it collides with the block on the right, will be the same as the initial velocity of the block on the right. It will take the velocity of 0 from the middle block. We can extend this trading speeds idea further. Since the block in the middle was initially at rest, it will take the initial speed of the block on the left. In other words, after they collide, this guy will be moving to the right at 6 meters per second. It will then collide with this other block with the same mass, 4 kilograms again, and they will stick together, which is what we call a completely inelastic collision. After that, we can use momentum conservation to try to figure out how fast they will move as an 8-kilogram unit. Starting from our momentum conservation analysis, we'll use m times v for each block separately before they collide. After they collide, you could write this as mass of block B times v prime of block B plus mass of block C plus times v prime of block C, but they have the same v prime. In other words, they move with the same velocity after colliding, and therefore all I've done is just factored out this v prime. You don't have to do it this way, but I think it's a little easier. Subbing in the numbers we know, the initial velocity of block C was 0, so that goes away. And we know the initial velocity of block B was 6 meters per second because, again, it stole the velocity of block A after they collided elastically. And therefore, your total momentum in the system is 24 kilogram meters per second, both before and after the collision. So once the mass in motion changes from 4 kilograms to 8 kilograms, the velocity changes correspondingly so that the total momentum is conserved, giving an answer of 3 meters per second, or C. This is a pretty straightforward calculus question. The only part of it that might make it slightly trickier is that you're asked to find the net force, not just the acceleration. So let's first set up a formula for net force, which is Newton's second law. And if I replace this with some of the known values, m is just m, right? We said that in the prompt up here. It's just m, so that stays as it is. A is what we need, though. We don't have a formula for a, but we have a function here for velocity with respect to time. So we just take its derivative. And this is basic power rule stuff. Because it's the derivative of velocity with respect to time, I bring my 2 out front. B is a constant, so it's 2bt to the first power, or just 2bt, and then c is a constant, so its derivative is 0, and I'm left with 2bt. That goes into Newton's second law up here. M stays as m, like we said earlier, and your final answer is 2bmt, and then we evaluate that at time t sub 1, because that's what the prompt tells us to do, and your final answer is therefore E, 2mbt sub 1. Starting from kinematics, we're going to have to split this into different intervals of time, and I want us to be very clear about what period we're talking about, so I'll put this at the top. So from 0 to 1 second, I'm going to use subscripts as well to denote what moment in time I'm talking about. So x sub 1 literally means the position of the object at time 1 second, and x sub 0 is the position at time 0, not just the general like starting position. We often use 0 sort of incorrectly to mean like the beginning of any interval, regardless of what time an object starts at. So here 0 literally means time 0. Anyway, same goes for velocity 0, t plus 1/2 at squared. So this is just a kinematic equation we've been using all year. We also know the starting position and starting velocity at time 0 both to be 0, so those terms go away. And we know that the time change from 0 to 1 is 1 second. So you solve this for acceleration, and now we know the acceleration is 2 meters per second squared, and we can apply that to a new interval, 1 to 2 seconds. So I'm going to change the subscripts now to denote what moments I'm talking about. Just like I did in the first column over here, only you'll notice now this is no longer x sub 0, but it still means initial position. Only initial in this case doesn't refer to time 0, it refers to time 1. That's why it's important to have these subscripts. So anyway, the position at time 2 is equal to the position at time 1 plus the velocity at time 1 times the change in time, and that'll be important in a moment, plus 1/2 a change in time squared. So we can't just say x initial position and initial velocity are 0 because they aren't. They aren't 0 at time 1. We actually have to find them. We can also sort of simplify this by subtracting x sub 1 to both sides, from both sides, and then on the left side we end up with x2 minus x1, and that's the same as the change in x, or the displacement. So my displacement is velocity at 1 times 1 second. Now you'll notice I put a 1 here, even though my final time is 2, because we're not talking about the final time. We're talking about the change over the interval being analyzed, and that's a 1 second change from t equals 1 to t equals 2. We still have two unknowns, though. We're trying to find displacement, but we don't know the velocity at 1, so we have to find that first. So we're going to have to first figure out the velocity at time 1, and to do that I want to analyze the intervals 0 to 1 second because we know more information. For instance, we know the velocity at time 0 to be 0, so that can be simplified. We already found the acceleration, and the change in time is again 1 second. We now know the velocity at 1 second is 2 meters per second, which can go in for v1 in the other column over in this equation. Alright, here you have it. Now we can solve for displacement during this interval. We get 2 times 1, which is 2, plus 1/2 times 2 times 1, which is 1. All of that simplifies to 1. So your total displacement for this interval is 3 meters. This is the alternate solution where you can use proportional reasoning. Specifically, the proportionality here is that the position is proportional to the square of time. So, by the way, that's true of all objects that accelerate uniformly. In 1 second, we already know that we traveled 1 meter. So if you use proportional reasoning, you could sort of say in 1 second I travel 1 squared meters, which is still 1, but that'll be more important once we switch to a different period of time. In 2 seconds, then, you'll travel 2 squared meters. Now that, to be very clear what I mean by that, you will travel 2 squared, or 4 meters, in the interval 0 to 2 seconds. So if in 1 second you're at position 1 meter, and if at 2 seconds you're at position 4 meters, your difference is 3 meters, and that's the same answer that we just found with kinematics. This question is a lot simpler than it might look. I'm going to try to draw it and hopefully help you understand what's going on here. Okay, so we're going to try to cross this river from point A to point B, which is straight across, but the current is trying to push the boat downstream. So what would happen if the captain aims the boat directly at B, sort of forwards? Will he land at B? No, I think it's clear why, because even though you're aiming straight, the river is also contributing to your motion. So your total velocity is the resultant of the velocity of the boat with respect to the water, which is straight forwards, and the velocity of the water with respect to the land, which is straight to the right. Straight to the right. And the resultant of those two is the diagonal from A to C, and we just saw the boat follow that path. So we want to answer the question, is it even possible for a boat to cross a river from A to B with a current? And the answer in general is yes. In the generalized version shown, if you angle your boat somewhat upstream, you can still cross directly from A to B, or right across the river without moving downstream. That's not necessarily the answer to number 7. I just want to make the point that it's possible under the right circumstances. So now we want to figure out, is it possible in this problem? So what we need is a component of velocity that is directly against the current, and that will effectively cancel out what the current is trying to do, pushing us downstream. And whatever component of velocity is remaining will be pointed towards B, or across the river, up in this image, and that will be the velocity at which we cross the river. So if we try to look at this from a vector standpoint, your total velocity will be at this diagonal. That's the hypotenuse of the right triangle here. The down leftwards component here is going to be upstream, and we need that to be the same as the river current speed. Whatever remains of your velocity is the part aiming at B. That is the speed at which we will cross the river. So here's my boat. My total boat speed is 5 kilometers per hour. But we also said that we needed this bottom side of the triangle, the upstream component of velocity, to match the river current. This has to be 5 kilometers per hour. And if the hypotenuse of the triangle is 5, then this side of the triangle has got to be less than 5. Man, that's just how triangles work, right? So that is basically the answer to the question. Even if this captain only tries to drive the boat perfectly upstream against the current. The best he could ever do would be to not move. He can stay in one place, but the instant he angles his boat towards B, towards the other bank of the river, he will have an insufficient upstream velocity to counteract the river current, and therefore he will move downstream if he crosses the river. In other words, it's impossible for this boat to reach the other shore. All right, this is a vector addition question, so let's try to blow up these arrows so we can see what's going on. Here you have V1 and V2, and what the question asks is, what would you have to do to V1 to turn it into V2? It asks about the acceleration, really, but the acceleration is just the change in the velocity. So a way of sort of understanding what this is asking is, if you start with V1 and you want to end with V2, what would you have to add to V1 to get V2? What's the missing piece here? And so we're not going to add these tail to tip, and the reason is that we're not starting with two vectors and then trying to find their resultant. We're starting with one vector, and V2 is the resultant. This is the final answer. We want to know what is sort of the missing vector that has to be added to V1 to get the resultant V2, and that is where we use tail to tip. So the acceleration vector completes the triangle and looks like this. Therefore, the answer is directed north of west.